Very good. So hello everybody. So it is my pleasure to introduce José Ignacio Burgos from ICEMAT in Madrid. He's going to talk us about Chernobyl theory and Hilbert-Samuel theorem for semi-positive singular toroidal metrics on line bundles. So you may go ahead.
Okay, so thank you very much. Let me start by thanking the organizers to invite me. It's always a pleasure to be in Zoom, and I will start talking. So I have to say that this work I want to present is joint work with Ana Maria Botero, David Holmes, and Robin de Jong. And just 1 second. So in the first part, I will introduce the main objects of the talk and the main result that will be B divisors, graded linear series, and PSH metrics in the toroidal setting. And then in the second part, we will see applications to the line bundle of Siegel-Jacobi modular forms. So let me start recalling what are toroidal B divisors. So we start with a smooth complex variety. Let's say it's a projective one. And I take B inside X, a simple normal crossing divisor, a reduced one. Then to this pair X and B, one can associate a conical complex, a conical polyhedral complex, which is called the Clement Complex. And for instance, is explained in the famous monograph by Kempf, Mumford, and collaborators, toroidal embeddings. And basically, it's a generalization of the dual graph of a semi-simple curve. So you take one ray for each component of the divisor, then you take a two-dimensional cone for every irreducible component of an intersection of two divisors, then a three-dimensional cone for every component of a triple intersection, and so on. And this conical polyhedral complex recovers, in some sense, the incidence relation between all the components of the simple normal crossing divisor. Then I take as div of XB. This will be the group of Cartier divisors with real coefficients. So we can do the same with the integral or rational coefficients, but I will stick to real coefficients on the variety X that have support exactly on B. So this will be just formal linear combinations of components of B. And then I will denote by R of XB. This will be the set of all allowable modifications of this pair XB. This means that these are modifications of X, but such that the centers of the blow-ups have to be toroidal. So I am allowed to blow up, for instance, the intersection of two components or an irreducible component of a triple intersection, and then I can go on and always making blow-ups in intersection of components. And it turns out that the theory of this conical polyhedral complex tells me that these allowable modifications of XB are in one-to-one correspondence with rational subdivisions of the Clement complex. So for instance, if I blow up in an intersection of two components, this will be just to add one ray in the cone defined by these two components. And then one defines the space of toroidal Cartier B divisors related with XB. This will be the direct limit for all possible modifications. And one can see that this direct limit is in bijection with the set of all piecewise linear functions on the Clement complex, such that if I take the fan of linearity of this linear function, has to be rational, has to be defined over the rational numbers. This will be the direct limit, but one can define also the space of Weil B divisors, of toroidal Weil B divisors, and this will be the inverse limit with respect now to the push forward of divisors of the divisors on different components. This is a much wilder set, and in fact, it can be put in bijection with a set of all conical functions defined on the rational rays of the Clement complex. But here is all functions, so there is no continuity, nothing at all, it's just conical functions. In particular, a toroidal Cartier B divisor, since it is a direct limit, it is just to choose a divisor in some modification. So a Cartier B divisor will always live in a fixed modification and will be given by a divisor in this modification with support on the pre-image of B on this modification. This will be BP. while a while B-divisor is a collection of choosing a divisor on each modification, but all these divisors have to be compatible in the sense that if I have a map of modifications from xp prime to x pi, then I ask that the direct image of dp prime has to be equal to d pi. So these are, in some sense, the concrete realizations of the space of toroidal Cartier B-divisors and of Weil toroidal B-divisors. So the Cartier ones are just choose a B-divisor in a modification of X, while a Weil B-divisor will be to choose a tower of divisors, one on each modification, but this tower has to be compatible under push forwards. So I have described the case of toroidal B-divisors that we just restrict only to toroidal modifications and divisors supported on the original simple normal crossing divisors. But of course, one can play the same trick or the same history looking at all possible modifications. So then there is a theory of just Cartier B-divisors and Weil B-divisors, not necessarily toroidal, and then the limit will be taken over the category, for instance, of all smooth and projective modifications of the original variety X. We can take the smooth projective because this will be a cofinal set. Okay, but these are the B-divisors, so are divisors defined in a modification of X. Now, on B-divisors, we can restrict our attentions to the numerically effective ones, the NEF B-divisors. So we have that the Cartier divisors and the Weil B-divisors, these are defined as direct limit and inverse limit of vector spaces. These finite dimensional vector spaces have a natural topology, and then I can take the limit in the category of topological vector spaces. So then the space of Cartier divisors and the space of Weil B-divisors have a canonical topology. So for instance, in the case of Weil B-divisors, the topology that we obtain is that the topology of point-ways convergence. Now, using the fact that every time I have a modification, it is true that if I take the pullback of a divisor and then I make the push forward to the original variety, I get the identity. This easily implies that there are inclusions from the set of divisors in a concrete modifications to the set of all Cartier B-divisors, and then this is included in the set of all Weil B-divisors. So we have this inclusion. So the Weil B-divisors include all the Cartier B-divisors. And we will denote by div x pi b pi plus the subspace of NEF divisors. And then b Weil divisors plus will be just the closure of the union of all divisors that are NEF in a particular realization. Not that this is the closure in the topology. The topology of point-ways convergence is a very wild topology. For instance, it is not sequential. But if one restricts to the theory of NEF divisors, the convergence is much nicer, and we have this theorem that is due to Ana Maria Botero and myself in the case of toroidal B-divisors, but it is also due to Dan and Fabre in a much more general setting that tells us the following thing. So if I start with a NEF Weil B-divisor D, then we can find always a sequence of NEF B-divisors in different modifications. So in principle, since it is in the closure, I will be able to find a net, but here we can really find a sequence of divisors that converge to D, and not only converge to D, but converge monotonically to D. So for instance, we can take a decreasing conversion to D. And then if we take now the self-intersection of these divisors with themselves, so I take D alpha to the power D, where D is the dimension of X, and now I take the limit when alpha goes to infinity, then this limit exists, is always a real number, and it is independent of the sequence that I choose to converge to D. Hence, I have a well-defined degree of Weil B-divisors. So if you think a little bit, it is easy to multiply one Weil B-divisor with a bunch of Cartier B-divisors, or it is easy to multiply Cartier B-divisors. But in general, the product of two Weil B-divisors is impossible to define because this is a so wild object. But if we restrict the attention to the NEF Weil B-divisors, then there is a well-defined degree that can be constructed just as a limit using an approximating sequence. Now, the next actor in the picture are graded linear series. So now we start again with a complex variety that I am always assumed to be smooth and projective. Then I take F, that will be the field of rational functions on my variety X. And then a graded linear series is just a graded subalgebra of the polynomial ring in one variable with coefficients in this field F. Then if I have a finite dimensional subspace L in the field F, so this will be, so my variety was over the complex number, so this will be a finite dimensional complex vector space. Then we can define the graded linear series defined by L will be just the subalgebra of Ft that is generated in degree 1 by L times T. So it's generated in degree 1 by a finite dimensional subspace. Then one says that graded linear algebra is of integral type if there exists a finite dimensional subspace L such that AL is contained in A and A is finite over AL. So A is very close to be generated by a finite space in dimension 1. And then we will say that graded linear algebra A is of almost integral type if it is contained in an algebra of integral type. Then we'll use the following notation. Whenever I have a graded linear algebra A, this is a subalgebra of the polynomial ring, then I will denote the piece of degree L as AL. So A will be the direct sum of AL times T to the power L. And AL will denote the piece of degree L. The basic example of a graded linear series, if I have an honest divisor in a variety, I can take L of D is just the set of rational functions such that the divisor of F plus D is effective, union 0, and this is a group. And then R of D will be the sum for all L of LD times T to the L. And this guy is always a graded linear series of almost integral type. So here we can take functions tensor with R. So this L of D will give us a group, and we tensor with R to get a vector space and get a graded linear series. Now, the third actor in the picture, so we have B divisors, we have this graded linear series, and then we go to the third actor in this play, that are the toroidal singular Hermitian metrics. So again, we have our complex manifold, we have our normal crossing divisor, and U will denote the complement of B, and L is a line bundle on X. Then a singular metric on the line bundle L is called a PSH toroidal metric with respect to the fixed divisor B if it satisfies the following properties. The first property is that the metric is continuous on U. So this is just for simplicity. In fact, we only need that the metric is locally bounded on U, but let's assume that it is continuous on U. Then the second condition is that for every point of X, if I choose a generating section of the line bundle on some small open neighborhood around X, and I consider the function f to be minus log of the norm of the section, then this function has to be PSH, which means that it might have the value minus infinity, but not the value plus infinity. So it's a function from B to R union minus infinity. It has to be upper semi-continuous and locally integrable, hence it defines a distribution. And then if I take the derivative DDC, the second derivative of f, in the sense of distribution, this will be a positive curve. So this is one possible definition of being PSH. And then, so these two conditions will be just to have a semi-positive metric, a semi-positive singular metric. But in order to be toroidal, we have to add the third condition, is that if this open set B is not just an open neighborhood of X, but is a coordinate neighborhood that is adapted to the divisor B, which means that the intersection of B with the divisor is just the product of coordinates set 1 times set k equals to 0, then the function f minus log of the norm of s squared can be written as a function g that only depends on minus the logarithm of the first variable up to minus the logarithm of the variable zeta k plus a function eta that depends on all variables in such a way that the function eta is locally bounded and the function g is a convex function. So this will be a PSH toroidal metric. So the idea is that the singularities are not arbitrary, but the singularities are given by this convex function that only depends on the norm of the variables Z1 up to Zk that define the divisor. Any questions so far? Okay, now we have these three actors. So we have on one hand this toroidal singular Hermitian metrics, we have this graded linear series, and we have these B divisors. And we want to see how they interact with each other, how they are related. Now we can go from toroidal PSH metrics to B divisors. So if I have, again, the same setup as before, my complex projective identity X, my boundary divisor B, the complement U, a line bundle, then I have a rational section, and I have a metric, which is PSH and toroidal. Then one can define a B divisor, B of L, S, and the metric, which basically is taking the divisor of S in L, but then we add a correction given by the metric, and this correction is defined by the log numbers of this function f equal to minus log of s. So these log numbers are some numbers that measure the singularity, and this depends on the singularity. So I don't want to enter in the definition of the log numbers, but at least to give a small a description of how this divisor is defined. So first, a property is that this divisor is a B divisor, in general, a Weil B divisor, but since our metric was PSH, this Weil B divisor will always be F and will always be possible to approximate by a sequence. And not only is F, but since the singularities of my metric were toroidal, so if I consider this divisor D and I subtract the divisor of the section, so just the algebraic divisor, this is always a toroidal B divisor. And in order to describe this B divisor, recall that I told you at the beginning that any B divisor and any toroidal B divisor can be described by the function that determines in the Clement complex. Well, this divisor D minus ds corresponds to a conic function phi of D on this Clement complex, and this function is given as follows. So if I have B a coordinate neighborhood, and the intersection of the divisor or the boundary divisor with B is given by Z1 up to Zk equals to 0. So this will be a component of a kth intersection of components of my divisor. Hence, it will correspond in the Clement complex to a cone of dimension k. Then I will have the stratum S, which will be Z1 up to Zk equals to 0. This is a stratum of the boundary divisor. It corresponds to a cone sigma S of dimension k in this Clement complex. Now we write the function minus log of the norm of S, where I assume that S is generating in this open set as my convex function G plus a locally bounded function eta. Then the B divisor is encoded by this convex function G. In fact, the function phi restricted to sigma S is what is called the recession function of G, which is defined as the limit when lambda goes to infinity of 1 over lambda times G of lambda x. So observe that G is a convex function. If I look at this limit, the limit when lambda goes to plus infinity of 1 over lambda G of lambda x, this now is a conic function defined on the complex. So it's a little bit like going very far from my cone and looking at the function, at the asymptotic growth of the function. So how this function G behaves at infinity. And this is exactly how one constructs this B divisor associated to a singular metric. So it encodes the singularity, the asymptotic of the singularities of the metric close to the divisor. Now we have seen how to go from singular metrics to B divisors. We can also go from graded linear series to B divisors and vice versa. So if I start with a graded linear series of almost integral type, then I can define a B divisor associated to A. And this B divisor will be a Weil B divisor. So I have to specify one divisor on each modification of X. And then the B divisor on a particular modification. So let's say that my modification is X pi. Then I will look at all divisors on X pi. that satisfies that whenever I look at L times E plus the divisor of F has to be positive, has to be effective for every integral number L and for every function F that belongs to the graded linear series A of degree L. And this infimum is taken component-wise. So I take the infimum of every component of E. In general, if I start with any graded linear series, there is no reason why this will be a toroidal B divisor. So in general, this will be a B divisor, not necessarily toroidal. And vice versa. If I start with a B divisor, I can define a graded linear series as follows. So I so I will define L of D, just copying what is done in the case of ordinary divisor. So I look at all functions such that D of pi plus the divisor of F is effective for every modification, and then I add C. And then the graded linear series will be just take the direct sum for all the multiples of D of this L of D. So we can go from graded linear series to B divisors and from B divisors to graded linear series. Finally, we can also go from toroidal PSH metrics to graded linear series. So again, we are in the same setting. So X is my projective complex variety, B my boundary divisor, U is the complement, L a line bundle, and I have a singular PSH metric, and I have a section as before. Then I define the L of the line bundle, the section, and the norm. This will be the space of all rational functions, such that when I multiply F times S, this will give me a new rational section of the line bundle. Then I ask that the norm of this section is bounded. So the graded linear series is given by the bounded sections of the line bundle, bounded with respect to the norm. And then R of L, S, and the norm will be just the direct sum for all this bounded section in all possible powers of the line bundle. Then, so we have seen that we can go from PSH metrics to graded linear series, from PSH metrics to B divisors, and from graded linear series we can go to B divisors, and from B divisors we can go to graded linear series. But this construction is not always commutative, so we only have some compatibilities. For instance, if I have that a B divisor is smaller than another one, this means that D prime minus D is effective, then the graded linear series associated to D is contained in the graded linear series associated to D prime. And in the other direction, if I have a graded linear series A that is included in a graded linear series A prime, then the B divisor associated to A is always smaller or equal than the B divisor associated to A prime. Now, if I start with a B divisor, I look at the graded linear series defined by the B divisor, and then I go back to B divisors. In general, I will not recover the original B divisor. What I can only say is that the end result will be smaller. So the final B divisor will be smaller than the original one. And similar, if I go in the other direction, if I start with a graded linear series, I look at the B divisor associated to this graded linear series, and then I go back again to the graded linear series. The only thing I can say in general is that my original graded linear series is included in the final graded linear series. Other compatibility is that if I start with a singular PSH metric, I take the associated B divisor and I look at the associated graded linear series, or I go directly to the graded linear series, then I have an inclusion. So in general, they don't agree, but I only have an inclusion between the graded linear series associated directly to the line bundle with a metric and the graded linear series obtained going through the B divisor. But if we are in the toroidal case, then things are slightly better. And for instance, if B is the boundary divisor, then we have also an inclusion in the other direction, but with a small epsilon. So if I take the B divisor associated with the line bundle, the section, and the metric, and I subtract a very small multiple of the boundary divisor, and I look at the graded linear series, then this graded linear series will be contained in the original one. So we have, in some sense, a sandwich where the graded linear series associated to the metric is contained in the graded linear series associated to the B divisor and contains the graded linear series associated to the divisor minus a small multiple of the boundary B divisor. And this makes things in the toroidal case much easier. For instance, we have the following properties. So if I start with a pile B divisor, let's say it is NEF, then I can define the volume of the B divisor as the limb sup when L goes to infinity of the dimension of the piece of degree L of the Graded linear series associated to B divisor, and then divided by L to the D and over D factorial. So this is just the analog definition of the volume of a classical divisor. And we'll say that my by B divisor is big if and only if the volume is strictly positive. So there are a lot of elements in the associated Graded linear series. Then we have a theorem with Botero and Holmes and de Jong that tells us that if I have a divisor that is at the same time big and NEF, then we have the equality. So if I start with the B divisor, I look at the associated Graded linear series and I take back the original B divisor, then I recover the original one. So this is an improvement from the general result that I only have an inclusion. So if I start with the divisor, look at the Graded linear series, and then look at the B divisor, I only in principle have that this is smaller than the original one. But if I start with a big and NEF toroidal B divisor, then I recover the original by B divisor. And as a corollary, if I start with a line bundle with a toroidal PSH metric, not just any PSH metric, a toroidal PSH metric, and I assume that the divisor associated to the section and the metric is effective, and that the boundary divisor is contained in the support of this B divisor, then it is true that if I start with my metric, I look at the Graded linear series associated to the metric, and then I look at the B divisor, then I obtain exactly the same result as going directly to B divisors. So in this sense, the theory of NEF and big B divisors have much nicer properties than the general results. And in particular, we have the following proposition that will be important later, is that if I have a Graded linear series A that is finitely generated, then the associated B divisor is always Cartier. So if it is finitely generated, then it will be explained by a finite number of sections, and then this will imply that the associated B divisor will live in a fixed modification, and it will be a Cartier B divisor. So it will not be an arbitrary Weil B divisor, but it will always be Cartier, which in particular implies that if I look at the associated function, the function in the Clement complex that is associated with the B divisor D, the B divisor associated to the Graded linear series A, this function will always be piecewise linear. So we can detect that a Graded linear series is finitely generated because the associated function of the corresponding B divisor will be piecewise linear. So we'll have to remember the result because it will be useful later. And the main result of this theory is that we can recover, going to these B divisors, we can in some sense recover the Chernobyl theory and Hilbert-Samuel theory. So the result, again, is joint work with Ana Maria Botero, David Holmes, and Robin de Jong, is that if we have X and B as before, we have a line bundle provided with a PSH toroidal metric. And just for simplicity, we will assume that the metric is smooth on U. So it's smooth in the complement of B, and all the singularities are on B. Again, this is a too strong assumption, so we only need it to be locally bounded on U, but then one will need to use a little bit more analysis. But let's, for simplicity, assume that it is smooth on U, and I take a section of the line bundle L. Then I can construct the B divisor associated to this section and this norm. This B divisor will be effective, and hence it has a well-defined degree, as I was explaining before. So I can compute the intersection of this divisor. Now, this intersection can be computed as the integral on the open set U of the first chain form of the line bundle on the metric to the power D. In general, if we have a more singular metric that, for instance, is continuous or is only locally bounded on U, then here I will have to use what is called the non-pluripolar product of a PSH current. So the C1s, the first chain form, will no longer be a form, will be a current, but it will be a positive current, and then we will need to use Bedford-Taylor calculus to compute the product, and one will need to make the integral along X of the non-pluripolar product of these forms. But with the assumption that the metric is smooth on U, I only need to compute the integral on U. And this integral, again, is just exactly equal to the volume of the Graded linear series. So you can see that, in some sense, the left-hand equality is a particular case of a chain-bell theory, where let's say topological or algebraic invariant, which in this case is the intersection of the divisor with itself, is given by the integral of a differential form coming from the metric, while the right-hand side equality is some analog of the Hilbert-Samuel theorem. It's an extension of the Hilbert-Samuel theorem that tells me that the growth of the number of sections in this Graded linear series is just explained by an intersection product. It's just the intersection product of the divisor. The point is that in this case, it's not the degree of the line bundle, it's the degree of the B divisor associated to the line bundle and the singular metric. Okay, so this is the main result in the theory. Any questions so far? Yeah. So if there are no questions, so let's go now to an application of this result, which is an application to the space of Siegel-Jacobi modular forms. So let me explain what are Siegel-Jacobi modular forms. So to this end, we have to start recalling what is the Jacobi group. So to explain what is the Jacobi group, let me start with the symplectic group. The symplectic group in dimension 2G with integral coefficients is the set of all matrices 2 by Z times 2 by Z matrices that can be written in block form with the 4 components. So these A, B, C, D are the 4 components in block form of the matrix, satisfying the properties that A transpose times C is equal to C transpose times A, which just means that A transpose times C is symmetric. Similarly, D transpose times B is equal to B transpose times D. Again, this just means that D transpose times B is symmetric. And then A transpose times D minus C transpose times B has to be the identity matrix. And we can embed the symplectic group in dimension 2G inside the symplectic group in dimension 2G plus 2 as follows. So I start in a block matrix A, B, C, D, and then I add some zeros and ones. So I take a big matrix where I have A 0, 0, 1. Here I have B 0, 0, 0, then C 0, 0, 0, and here D 0, 0, 1. So this is again now a symplectic matrix, but in dimension 1 more. So this is one piece of the Jacobi group. This is the symplectic group. Then we have the Heisenberg group. The Heisenberg group in dimension G is given by triples where lambda, mu, and x, where lambda is a raw vector of dimension G, mu is another raw vector of dimension G, and x is just a number. And I can embed this Heisenberg group also in the symplectic group is dimension 2G plus 2 as follows. So I have this block matrix with a lot of components, and then in the upper left corner, I put the identity 0, then the vector lambda and 1. In the upper right corner, I put 0, then mu transpose, mu, and x. In the lower left corner, I put the 0 matrix, and in the right corner, I put the identity lambda transpose 0 and 1. And this embedding is a morphism of groups. So in particular, I am telling you what is the group law in the Heisenberg group. It's just the group law inherited by the multiplication of matrices with this particular embedding. But now we have that the symplectic group can be embedded in a symplectic group of dimension 2G plus 2. The Heisenberg group can be embedded in the symplectic group of dimension 2G plus 2. And then the Jacobi group is just the semi-direct product between the symplectic group and the Heisenberg group as a subgroup of the symplectic group in dimension 2G plus 2. Observe that this way of embedding these two groups in this bigger group is telling me in particular what is the action of the symplectic group over the Heisenberg group and how this semi-direct product works. Now, the Jacobi group acts very nicely in some space. So we have first the Siegel upper half plane, which is just the set of all G by G complex matrices that are symmetric. So the S on top means symmetric, such that the imaginary part is positive definite. So this is the Siegel upper half plane. And then the Jacobi group acts on the product of the Siegel upper half plane times the vector space CG, the vector space of dimension G over the complex numbers. And the action is given as follows. So if I have a matrix in the symplectic group that is given by A, B, C, D, and then I have an element set in the Siegel upper half plane, and I have a vector W in C to the power G, then the action of M and lambda mu X on this point set W is given. On the upper half, on the Siegel upper half space, is just the usual modular action. So it's A set plus B times C set plus D to the minus 1. And essentially in the vector space is given by translations by the lattice. So W goes to W plus lambda times Z plus mu, but it's a little bit adjusted by the inverse of C Z plus D. So this is the action of the group on the upper half plane. And now we are algebraic geometers. So why do we care about this Jacobi group and this action on the upper half plane times C to the C? Is because if I take the quotient of the Siegel upper half space times, so I am taking the integral elements here. So the upper half space times CG divided by the action of this Jacobi group, what I recover is exactly the universal principally polarized abelian variety in the stacky sense, if I take the whole Jacobi group. If we don't like to work with stacks, then one can always take a neat subgroup. So a neat subgroup is a subgroup that on every representation, it does not have any eigenvalue that is a root of unity. So it's a subgroup that has universally no torsion. So I can take a neat subgroup and consider just the quotient by the neat subgroup semi-direct product times the Heisenberg. And this will give me really a universal family of polarized principal abelian varieties with some level structure in general. And just to avoid using stacks, I will assume always that I will consider a neat subgroup of the symplectic group. Then we can define Siegel Jacobi modular forms. So this is a generalization of modular forms. In the modular forms, we only have to consider the action of the modular group. Here in the Siegel Jacobi modular forms, we have to consider actions of the whole Jacobi group. So what is a Siegel Jacobi modular form? Is a Siegel Jacobi modular form. Now it has two invariants, is the weight K and the index M. So Siegel Jacobi modular forms of weight K and index M for a subgroup gamma of the symplectic group is just a holomorphic function defined on the upper on the Siegel upper half space times C to the G to the complex numbers, such that it satisfies the following transformation rule for all matrices in gamma. So F evaluated at M times Z W has to be equal to the determinant of CZ plus D. So this is the usual factor that one has to include in modular forms, but it has also a second cocycle that is depends on the index. So the first part, the determinant of CZ plus D depends on the weight. The second part depends on the index and depends on the linear part times the function F. So it's not invariant, but it satisfies this cocycle relation with respect to matrix M. And if I make the transformation rule with respect to an element in the lattice, lambda mu X, associated to ZW, then we obtain this cocycle that this part only depends on the index M. So it is not exactly an invariant function, but it's a function that satisfies certain cocycle relations. And finally, it has to satisfy some holomorphicity condition at infinity. And the holomorphicity condition at infinity reads as follows. It says that I can write down Fourier expansions of my function as a sum over all possible matrices that are symmetric and semi-positive definite and are half integral. This means that the elements of the diagonal have to be integral and the elements outside of the diagonal can be half integers. And all vectors are in set G of certain coefficients, C T of R times E 2 pi I divided over lambda gamma and the trace of T set and some other exponential factor. Now this depends on W and R. And this expansion, this lambda gamma is a suitable integer that depends on the group gamma and is the analog of the width of the cusp. But the important part is that the coefficient CTR is different from 0 only when the matrix 1 over lambda gamma T, 1/2 of R, 1/2 of R, and M is exactly the index, is a semi-positive matrix. And we will say that a Siegel-Jacobi modular form is a cusp form, so it vanishes a little bit more if the condition 3 reads that the Fourier coefficient CTR is different from 0 if the matrix 1 over lambda gamma T, 1/2 of R, 1/2 of Rm is not just semi-definite positive, but it has to be definite positive. So the only non-zero coefficients are when this matrix is strictly positive definite. Of course, depending on the group gamma, there will be what we can call different cusps. So one will have to make transformation of the function and look at the Fourier expansions on different cusps. But in the case of higher dimension, a big difference between the case of genus 1 and the case of bigger genus is the Cochlear principle. The Cochlear principle tells me that if G is bigger or equal than 2, then condition 3 in the definition of Siegel-Jacobi forms in some sense is not needed. So if I have a holomorphic function that satisfies condition 1 and condition 2, then it automatically satisfies condition 3. So the condition 3 is always satisfied if G is bigger or equal than 2. So we don't need to include it in the definition. Of course, if we want a cusp form, then we need to put this extra condition. But for Siegel-Jacobi forms, we don't need to add 3 because it is automatic when the genus G is bigger or equal to 0. Observe that this Cochlear principle is completely analogous to what happens in the case of Siegel modular forms. So in Siegel modular forms, we know that the modularity, if the genus is bigger or equal than 2, automatically implies that it is holomorphic at infinity. And there is a geometric explanation, very nice geometric explanation, that is the existence of the Satake compactification. So if I look at the moduli of principally polarized abelian varieties, and I look at the Satake compactification, this will be AG star, then the codimension of the boundary, the difference between the Satake compactification and AG is always bigger, the codimension of this boundary is always bigger or equal than 2. And the good thing is that in some sense a line bundle that is defined up to codimension 2 can always be extended. An holomorphic function that is defined up to codimension 2, it always can be extended. And this explains why the condition 3 is spurious in the case of Siegel modular forms. So one is tempted to think whether this existence of a Satake compactification is also true in the case of the Siegel-Jacobi modular forms. Now, since we are algebraic geometers, we want to interpret the Siegel-Jacobi form not just as holomorphic functions on the upper half plane, but a section of a line bundle. So now let's take gamma to be a neat subgroup of the symplectic group of finite index. And then we write AG of gamma. This will be, in some sense, the moduli space of principally polarized abelian varieties associated with the level structure given by gamma, which is just the upper half space divided by the action of gamma. And then U of G, the universal family, will be AG times CG divided by the Jacobi group associated to gamma. Then conditions 1 and 2 tells me that the function f in some sense is determined by a cocycle on gamma cross AG set for this group, hence of a line bundle on this UG. So there is for a fixed K and M, as long as my subgroup gamma is neat, then I have a line bundle L of Km of gamma, which is a line bundle on this universal family of abelian varieties. And the Siegel-Jacobi forms of weight k and index m, jkm of gamma, are sections of this line bundle. So in particular, we have that the space of Jacobi forms, that is denoted jkm of gamma, this space is contained in the space of global sections of this line bundle on this universal family. And the Cochlear principle tells me that we have an equality when G is bigger or equal than 2. This line bundle is very interesting because, for instance, if I restrict the line bundle LKM to a fiber of the universal family, hence it is a polarized abelian variety, then LM is 2m times the line bundle associated with the principal polarization. So is this Jacobi line bundle, in some sense, is a hybrid between modular forms on the base. So a modular form on the base, the pullback of a modular form on the base will give me a Siegel-Jacobi form of weight k and index 0, and the line bundle of the principal polarization, let's say the Poincaré bundle on the fibers. So it's a very interesting line bundle from a geometric point of view. And now we can ask several questions about this line bundle. So for instance, it is very easy to see that if I consider the algebra of all possible Siegel-Jacobi modular forms, so this algebra is not finitely generated. This is very easy to see because, on the one hand, one can prove that for index m bigger than 0, the space of Siegel-Jacobi forms of index m and weight exactly equal to 0 is 0. So there are no Siegel-Jacobi modular forms of weight 0 and index strictly bigger than 0. If we take index 0 and weight 0, then we get the constants. But for weight 0 and bigger index, we have none. On the other hand, if I look at a fixed weight k, then I can always find an arbitrarily big index m, such that the space of Jacobi forms of weight k and index m is non-empty. Now imagine that I have a finite set of generators. So this finite set of generators will have bounded ratio between m and k. And then the possible combinations of this finite set of generators will have bounded ratio between m and k. Because when I take the product of two modular forms of different weight and index, what we get is the sum of the indexes and the sum of the weights. But here we see that if I fix k, then I can take m arbitrarily big and get non-zero elements. Hence, the ratio between the index and the weight is not bounded. So there is no way I can get a finite set of generators for this. On the other hand, instead of looking at the set of all possible Jacobi forms of arbitrary weight and index, I can fix the ratio between the weight and index. So I can start with a weight k and an index m that are strictly bigger than 0 both. So k and m are both strictly positive. And then I can look at the sum for all integrals L bigger than 0 of the Jacobi forms, of the Siegel-Jacobi forms of weight L times k and index L times m with respect to the group gamma. And then I can ask whether this algebra is finitely generated or not. So the previous argument does not tell me anything about this one. So this one can be perfectly finitely generated. And in particular, a question which is related with this one is whether there is a Satake type compactification of the universal family of abelian varieties when the genus G is bigger or equal than 2, in such a way that the codimension of the boundary that I have to add is bigger or equal than 2. And that then my line bundle, LKM, extends to an, let's say, an ample line bundle in this Satake compactification. Observe that if this question, the second question, were true, then it will imply that the first question is also true. And the fact that this thing exists is very tempting because it will explain by geometric reasons why the Cochlear principle holds for Siegel-Jacobi modular forms. And in fact, there is a paper in 95 of Bernd Runge, theta functions and Siegel-Jacobi forms, where he studied a lot of properties of Siegel-Jacobi forms. And in fact, he states that the answer to both questions is positive. So he constructs a Satake type compactification of the universal family of abelian varieties, and he used this attack type compactification to prove that if I look at some linear algebra, some algebras of fixed ratio between index and weight, they are finitely generated. But the aim of this talk, in some sense, one of this talk is to disprove this known result. So in fact, the opposite holds true. So the algebra, this direct sum for all L bigger or equal than 0 of GLK GLM, so GLK LM is never finitely generated whenever K and M are both positive. And in particular, this implies that it cannot exist as a Teke-like compactification of the universal family of principally polarized abelian varieties. Then another question we can ask is, for instance, to compute the dimension of the space of Siegel Jacobi modular forms. Of course, this question is very difficult to get a closed formula for all possible indexes and weights, so we can be satisfied solving a much easier question, that is to compute the lim sub of this dimension. So to compute what is the asymptotic growth of this space of dimensions. So what is the lim sub when L goes to infinity of the dimension of J, of course, here is an LK times LM of gamma divided by L to the D factorial, when here now D is the dimension of the universal family of principally polarized abelian varieties. This is G plus G times G minus 1 over 2. So this is the dimension of the universal family. In fact, this question was answered much before than the theory of Siegel-Jacobi forms was completely developed, and this was solved by Tai in 82 using works also by Manford. And the formula, the asymptotic formula is as follows. So this dimension is given by the index of the group gamma with respect to the symplectic group, and then the weight to the G, the big G, G is G times G minus 1 over 2, times the index to the small g, then the dimension factorial, and then there's a sign, but this sign in some sense is spurious because it comes by this representation. Here we have the product from 1 to j of all values of the Riemann zeta function in negative integers divided by this factorial. Or if you prefer Bernoulli numbers, then one can write this formula as minus 1 to the d, the factorial, again the same m to the g, k to the big G, then a factor of 2, the index of the group, and a product where involves all Bernoulli numbers between 1 and g. So this formula was known by Tai in 82. But then the question is whether one can give an intersection theoretical interpretation of this form. So can we recover this asymptotic growth of the space of dimensions as an intersection number? And the analogy is that if I look at modular forms and I want to look at what is the asymptotic growth of the dimension of the modular forms, again, this instead of being a limit has to be a lim sub. Then the lim sub when L goes to infinity of the dimension of the space of modular forms is given by the degree of the line bundle of modular forms. So here MK is the space of Siegel modular forms and MK is just the line bundle of modular forms. And now the answer we want to give is that the answer is yes. So we can recover this dimension as a degree, but not as a degree of line bundle. It will be the degree of a B divisor. This is, in some sense, one of the reasons we're interested in B divisors. Now, what is the main tool to do this is to introduce the invariant metric on the line bundle of Jacobi forms. So how is defined the invariant metric on the line bundle of Jacobi forms? Is given as follows. So a section of the line bundle of Jacobi forms is given by a modular form, which is in particular holomorphic functions. And then I define the norm of this section as the absolute value of the holomorphic function, and then I multiply by the determinant of y to the k and this exponential factor, depending on the index, where if I have my element on the upper Siegel half space x plus I y, the y is the imaginary part of z, and the beta is the imaginary part of w. One can check easily that this value is invariant under the direction of the Jacobi group, so it really defines a norm in the line bundle of Siegel-Jacobi forms. And it's very interesting because this metric, in some sense, encodes the properties of the line bundle of modular forms. For instance, all the transformation properties of the line bundle of Siegel-Jacobi forms leave invariant this metric. Now, it's easy to check that if K and M are both positive, then this is a PSH metric, a semi-positive metric on U, on the universal family of abelian varieties. Now, there is the theory of toroidal compactification. So I can construct a toroidal compactification of the universal family. This is not a Satake type of compactification, so it's a compactification where the boundary divisor will be a divisor, will have codimension 1, and it depends on some combinatorial data that are given by a polyhedral complex inside a cone. But one can check that one can find toroidal compactifications such that the line bundle of Siegel modular forms with this metric that was PSH in the open can be extended to a line bundle on the whole space in such a way that the metric is still PSH when we see in the extended theory. So this is not obvious a priori, but one can construct particular extensions of the line bundle in such a way that the metric extends as a PSH metric on the whole space. Hence, we can apply the theory we have developed before, because this metric is not just a PSH metric, but it is also a toroidal PSH metric. This is, in some sense, the reason we were interested in the toroidal ones. And in particular, we can use this tool to prove that this algebra is not finitely generated. So let's see how the argument works. So first, we need a classical theorem by Ziegler that tells us that a holomorphic section or a Siegel-Jacobi modular form, so a holomorphic section of the line bundle of Siegel-Jacobi forms on the open space is a cusp Siegel-Jacobi form if and only if the norm of F is bounded. Hence, the space of Siegel-Jacobi forms is isomorphic to what we have defined as the Graded linear series associated to the line bundle of Siegel-Jacobi modular forms with this metric. So I put here that is this isomorphic instead of being equal, just because I have defined the Graded linear series as elements on the on the field, so it depends on the choice of the section S. Well, in the right, it does not depend on the section S. So this isomorphism is canonical and depends just on the choice of a particular section. And now we have a small lemma. Remember that I was saying that going from Graded linear series to B divisors is not always possible to go back. And this is an example where we have the Graded linear series of cusp Jacobi forms and the Graded linear series of all Siegel-Jacobi forms. And it turns out that the difference is so small that the associated B divisor is exactly the same. So these two divisors, these two B divisors are the same. But remember that we had a theorem that tells us that if I have a toroidal metric and we have the property that the B divisor associated to the metric and the B divisor associated to the corresponding Graded linear series was the same in the toroidal case. So we have that the B divisor associated to the Graded linear series of Jacobi forms is equal to the B divisor given by the metric. And remember that we have a proposition that tells us that if a Graded linear series is finitely generated, then the corresponding B divisor is Cartier. But now we know that this B divisor, the B divisor associated to the metric, can be described explicitly if we know how the metric works. So we can make an explicit computations, and we can, by an explicit computation, we can show that the associated function is not piecewise linear. Since the associated function is not piecewise linear, then as a consequence, this Graded linear algebra cannot be finitely generated, just because by an explicit computation, we can see that the associated function is not piecewise linear. And then for the other result, now we will use the Chern-Weil theory and the Hilbert-Samuel result. So now we know that the volume of the space of Siegel-Jacobi forms, which is exactly the asymptotic growth of the dimension of this space, is given by the degree of the associated B divisor. And the degree of the associated B divisor is given by an explicit integral on the open set UG of gamma of an explicit differential form given by the metric. And the good thing is that this integral can be computed explicitly, and we can recover Thijs' formula given the asymptotic dimension of this space. Okay, I think my time is over, so thank you very much for your attention.
Well, thank you very much. Are there any questions? So,
maybe I have a question.
Yeah, sure.
Sorry. I saw that you introduced the so-called toroidal passage matrix in this setting. As far as I understand, this is basically because in the mixed Shimura setting, you get this kind of similarities for line bundles. So I'm wondering if you have a similar definition for higher rank vector bundles.
That's a very interesting question, and not yet. So we would like to study what happens in higher rank vector bundles, but here things are much more complicated to get this combinatory. So the point is what kind of functions or what kind of objects you want to assign in this Clement complex. So for line bundles, they are just codified by a function in this Clement complex. But for higher rank vector bundles, things are not so clear. And for instance, one can try to imagine how to compute, for instance, the chain classes of the vector bundle, but I am thinking on it, but for the moment, I am very sorry that I am not able to answer this question. So it is a very interesting question, but for the moment, it's too difficult for me at this moment.
All right, thank you.
Yeah, thank you.
Any more questions? So I thought I saw someone raising the hand, but okay, so if there are no questions, thanks, Jose, again, and I will close the session.
Okay, thank you very much.
Thank you very much.